Over the last few videos, we've built a strong mental model for how logistic regression works. We used an example dataset where we tried to predict whether students would pass or fail exams based on the length of the exam and the amount of time they studied for it. We learned to think of the sigmoid not as an abstract function, but as a measure of a student's effort relative to a bare minimum required to pass. That bare minimum, where your chance of passing is greater than your chance of failing the exam, is represented by a line. This line is defined by three values, which we've represented as knobs that can be turned to adjust the position of the line and its associated probabilities. Finding better and better lines means repeatedly adjusting the knobs. How to best turn each knob requires peering into a landscape of possible lines, and learning to navigate using local clues. This video is simply about making that mental model more precise. There will be no walls of equations. We'll keep the visuals on screen and just label each idea with its corresponding mathematical name. Think of it like baking. We already know how ingredients interact to create different flavors and textures, but we haven't actually reached for measuring cups yet. This video is about walking through a specific recipe, the exact quantities and instructions that take us from understanding to doing. This is how I think about logistic regression. We know that a good line isn't just about not making mistakes. A good line is one whose probabilities match up with what actually happened. Aggregating the probabilities logistic regression assigns to our data lets us determine if we have a good line or a bad line. The likelihood function aggregates probabilities by multiplying them together, so that one small error where the model is confidently wrong makes the evaluation plummet. For example, look at how quickly the likelihood goes to 0 as we move knob 1. Similarly with knob 2. Simultaneously turning knob 1 and 2 and recording each likelihood value, we can map out the landscape of possible lines, where better lines are higher up in the landscape. We'll call knob 1 WST because it's the weight of importance of study time in the equation of the line. We'll call knob 2 WEL because it's the weight of importance of exam length. And we'll call knob 3 B, which stands for bias, to capture work that all students must do regardless of study time and exam length. These three values are called parameters, and they completely define the logistic regression model. The exact formula for the likelihood is the product of the probabilities logistic regression assigned to each student. In math, we write this probability as the probability of yi given xi, where yi is what happened to student I, either they passed or they failed, and xi is the study time and exam length for that particular student I. So this conditional probability is the probability that logistic regression would assign to whatever happened to that student, which we can calculate directly using the sigmoid and the parameters of the line. Navigating this landscape to find better and better lines means adjusting the knobs in such a way that we end up higher up in the likelihood landscape. But the likelihood function often shrinks to 0 exponentially fast, causing large portions of the landscape to be compressed into a tiny range of values. Meaning subtle changes in steepness are imperceptible in much of the likelihood landscape, making navigation challenging. So we need a way to amplify the imperceptible parts of the landscape without also amplifying its larger peaks. The logarithm is a function that does exactly that. It maps values between 0 and 1 onto the entire negative number line, spreading apart values that have been crowded together near 0. Applying the logarithm to the likelihood reveals details of the terrain that were previously difficult to see. Mathematically, notice that the logarithm changes the product of probabilities into a sum, which we'll see makes some math easier. This log likelihood landscape is much easier to navigate. But convention in machine learning is the best line should be at the lowest valley, not at the highest peak, because that aligns more with our intuition of reducing the number of mistakes. So we flip the sign to turn the landscape upside down. This landscape is called the negative log likelihood, because we took the negative of the log of the likelihood. But what you see here isn't actually the negative log likelihood, because there are 3 parameters and this is only relative to the first 2. Visualizing how the negative log likelihood changes as a function of all 3 parameters is tricky, but not impossible. Here, height corresponds to the negative log likelihood value for 2 of the parameters. In order to create space for the 3rd parameter, we need to visualize the height of the negative log likelihood differently. We'll do this using colors. By assigning a color gradient to each negative log likelihood value, now good values have darker blue colors and bad values have brighter pink colors. And now we don't need height anymore since we have colors, and we can represent this 3D structure in just 2 dimensions instead, which leaves room for the third dimension to be the third parameter. This is the slice of the landscape we were previously visualizing where the bias term was 0. As we change the bias term, we can scan the likelihood space to see its full structure, and we can do the scan in all directions. But we can also just color the entire space. Better lines are in the darker regions of the space. But this cube is just a small window into the infinite space of all possible lines. This window gives us local clues as to where darker regions of the space and thus better lines might lie. But only the darkest colors of this entire window help us navigate intelligently. So why not make the window smaller? And we can slide the window in a direction where the colors change to dark blue the fastest. But concretely, sliding the window means taking tiny steps to improve the line. And we might never reach our destination in time. But to some extent, this is the safest approach because who knows what the colors will look like far away from our window. If only we could know how reliable our local clues are so that we could take steps more confidently. That's foreshadowing, we'll get to that soon. But there's a subtle challenge. We need to be able to adjust how far we step depending on the terrain. Recall, if the curve is steep, leap. Far from a good line where the terrain is steepest, we can take larger steps because we expect a better return on investment. Close to a good line where the terrain tapers off, we might want to step more carefully, otherwise we might just end up stepping around a solution and never actually reaching it. So the size of our steps should depend on the steepness of the negative log likelihood landscape. But how do we measure steepness? Let's go back to our 3 plots, each showing how the negative log likelihood changes as we move each of the knobs, keeping the others where they are. Steepness is just how much the curve goes up relative to how much we go across. We use delta to mean change, so we can express steepness as the change in negative log likelihood relative to the change in parameter. But looking over a large range of parameter values isn't necessarily representative of the steepness at that specific point. Shrinking that range, we get more local estimates of the steepness. As it turns out, we can shrink it so much so that the change in parameter is effectively 0, providing us with the instantaneous steepness at that point. This is called a derivative. We can calculate these derivatives using the following formulas. The exact steps to get these formulas isn't really important and is more the topic of a calculus video. Each of these 3 values represents the steepness in each of the coordinate directions. But let's not stop here. The derivative relative to WST is negative 39. What does that actually mean? It means that at this location, the negative log likelihood is behaving as if changing WST by 1 unit would decrease the negative log likelihood by 39 units. The key here is that it's at this particular location only. The moment we change WST, the steepness will change and the actual decrease in negative log likelihood might be different. What's more, if we change other parameters, that also would affect the steepness of WST. But larger numbers convey a potential greater opportunity, more change in negative log likelihood for the same change in parameter. Negative numbers means the negative log likelihood will improve, positive numbers means it will worsen. We want to adjust the parameters in a way that will improve the negative log likelihood. Each parameter can either be increased or decreased. This is where the knob analogy shines. The sign of the derivative tells us which direction to turn the knob in order to increase the negative log likelihood. For example, if the sign is negative, like with WST, and we decrease WST, we'll end up increasing the negative log likelihood. So the opposite of the derivative is the greatest opportunity for improvement here, since our goal is to decrease the negative log likelihood as much as possible. This navigation process is called gradient descent. We start with a random assortment of parameter values, calculate the opportunity for improvement in each direction, then turn each knob accordingly. Concretely, each parameter will be updated by taking a step alpha in the direction opposite to the derivative. But recall, we want the step size to change with the steepness of the terrain. So we multiply alpha by the negative of the derivative so that larger opportunities for improvement naturally produce larger updates. Step by step, we update WST, then WEL, then B, and repeat. In practice, we don't update these one at a time. We combine each of the three directions into a single direction called the gradient, and apply updates to all parameters at once. Notice that even though our step size is constant at a value of 0.06, because we're taking steps relative to the gradient of the negative log likelihood, the jumps we actually make in the space vary in size. As we get better solutions, the changes to the parameters become smaller. But while being close to a solution usually means taking small steps doesn't always mean we're close to a solution. It may not look like it, but right now we're in a narrow diagonal valley. If we look only in the direction of WST, the landscape looks almost flat. Similarly with WEL. Turning each knob doesn't do much to improve the negative log likelihood, but turning both together in just the right combination can still move us along a better path. The gradient tells us what the terrain looks like right here, but it doesn't tell us how long that information will be useful. The problem comes down to how reliable our local information is. Will the steepness at this specific point suddenly change, or will it remain stable and reliable? Just how we measure change to the negative log likelihood relative to the change in the parameter, reliability is simply how much the derivative would change as we move it in different directions. For each derivative that makes up the gradient, we can turn each knob and measure how much the derivative changes relative to the change in parameter. If it changes a lot, that means that this local information is sensitive to the change in that parameter and may be unreliable. That measure of how much the derivative changes is essentially the derivative of the derivative. It's captured mathematically in a matrix called the Hessian. Remember that foreshadowing from earlier? This is how we measure that reliability, which we can use to improve our navigation. By measuring the stability of each derivative, we can adjust each component accordingly. Reliable directions get amplified, unreliable ones get de-amplified. This adapted gradient descent process is called Newton's method. While gradient descent had a zigzagging in the narrow valley of the negative log likelihood, Newton's method is able to find the valley and walk a straighter path within it. But sometimes, neither strategy works because the data is working against us. So far, we've been treating the magnitude of the derivatives as a measure of how much opportunity there is for improvement. But notice that the derivative relative to the study time weight, for example, depends on the study time values. If we measure study time in minutes instead of hours, nothing about the students would change, nothing about the exams would change, yet the derivatives would suddenly be 60 times larger, distorting the landscape in such a way that dark blue sections are harder to find. Gradient descent still works, but the path is skewed by the difference in scale. A step size that works for exam length is too big for study time, and a step size that works for study time is too small for exam length. The obvious solution is to inspect the dataset ahead of time and correct for issues in scale. You can think of this as undistorting the landscape. But sometimes the shape of the landscape is meaningful. It's a reflection of genuine structure in the data, not just mismatches in units. So another complementary solution which adapts navigation to the shape of the landscape is Newton's method. But even it has its limits, which we'll talk about in a later video. At this point, you know almost everything there is to know about how logistic regression works. But how well does it actually work? How do we know that the probabilities logistic regression assigns are actually representative of reality? And what does the model actually mean concretely? If a student studies an hour more, how does that impact their chance of passing? And how confident can we be in that statement? These will be the topics of future videos. Like and subscribe for more content like this.